All right, so this practice problem reads, suppose you need to raise a 250 kilogram mower a distance of 6 centimeters above the ground to change its tire. If you had a 2-meter long lever, where would you place the fulcrum if your force was limited to 300 newtons? Now, when this problem was given to me, for me to do a video on it, it's a little unclear to me what the distance 2 meters is representing. So we're actually going to solve this problem two ways. We'll see that they end up with very similar results. We're going to solve this problem two different ways. One where we consider that 2 meters the total lever arm distance, so the lever arm of the mower force and the lever arm of the force you're pushing down as a total distance. And the second is if we had a 2-meter long board that we put at an angle and it's the length of that board. So slightly different approaches to the problem. One is going to use our torque analysis. The other is going to rely on that idea of simple machines and work to see how we solve for it. So let's do that first problem where we have this board, okay, and we know that there are going to be two forces acting on it. We have the force of the mower and we have the force of you pushing down on it. We know that the force of the mower is equal to the weight of the mower. So that is, as a reminder, 250 times my 9.8. So 250 times 9.8 is 2450 newtons. So 2,450 newtons pushing down on that side. We're told that the force you exert is equal to 300 newtons. All right. So if we were to just place a pivot point, the fulcrum, there at this location, if we use this 2-meter lever at level as the distance between these two forces, then this distance, R1, and this distance, R2, is such that R1 plus R2 equals that 0.2 meters. All right, and then we can do a torque analysis on this problem. So let's look at both of our forces, force 1 and force 2, and we'll do that torque analysis. So torque 1 is equal to force 1 times radius 1. And we're going to use the I'm having a hard time saying that today. We're going to use the lever arm method. So this is actually L1. All right, when we do that, remember the lever arm, I'm really having a hard time with that word today, is the distance between the pivot point and the line of action, the perpendicular distance. So if this is our line of action, this is that lever arm distance. And we can see that's equivalent to R1 as I have drawn it. So that is the force 2450 times R1 for our torque by force 1. The torque by force 2 is the force you apply times the lever arm 2. And again, if we look at that line of action, that perpendicular distance, L2, is the equivalent of R2. Now, well, I guess I can put that in there to begin with. So we have 300 times R2 as our torque. So the net torque is going to be the sum of these two. We want to keep in mind, and you've probably noticed in the lever arm methods, I tend to go, forgot to look at that direction. So let's remind ourselves what those two directions are. The mower is trying to rotate this board in the counterclockwise direction. So the mower is positive, and you are pushing down in the clockwise direction. So you are acting negatively. So this is going to be a negative value. So we have 2450 times R1 minus 300 times R2, and that has to equal 0. Now, this is two unknowns, and I can't solve one problem with two unknowns, But I do have another equation. I know that R1 is equal to 2.0 minus R2. And so, yeah, similarly, R2 is equal to 2.0 minus R1. So which one might I want to use? Well, I want to know where to put that fulcrum. So we have to decide, do we put it a distance R1, or are we going to talk about it relative to U? Either way, the fulcrum's in the same spot. So I'm actually going to solve for R1, so I will use this lower value. So we have, oops, wrong color. We have 2450 times R1 minus 300, and I'm going to substitute this in for R2, 2.0 minus R1. That equals 0. So I'm going to distribute my 300. So this is 2450 R1 minus 600 plus 300 R1 is equal to 0. I can combine my terms, so I have 2750 R1 is equal to 600. So R1 is equal to 600 divided by 2750. And that gives us 0.22. R1 is equal to 0.22 meters. So if we put that at 0.22 meters, our system will be in equilibrium. All right? So that's one way to solve it. If we consider that 2 meters as this length. What if we consider that 2 meters as the length of the board? We have to think of this problem a little bit differently. So I'm going to go ahead and erase this part. We're actually going to come up with similar answers in both these methods because it is a 2 meter long board, and to reach that equilibrium value, the fulcrum is in fact pretty close to this side of the board. And so we're not going to get a whole lot different answers in our two methods, which is to be expected. But since I wasn't 100% sure how to interpret that 2 meters, might as well show you both methods. So, I just have to get this erased. So in the second method, we want to recognize the mechanical advantage of a lever system. And that tells us that if I put in a fulcrum, what I have to exert on this side is at a distance is less than what's being exerted closer to the fulcrum. And that's our idea of that mechanical advantage. So, oh my goodness, erase, erase, erase. All right, so the first thing that I want to then do is examine how that might in fact look. So if you imagine that we have, this is now our 2 meter long board, okay? And if I have my mower on this side of the board, and I'm going to push down on this side of the board at some fulcrum, okay? Don't know where it is. I'm just going to pop it there. I have a hint at where it is from that first problem, so I'll put it on that side. I know that the work done on this side, we're going to call this side A and this side B. The work done on side A has to equal the work done on side B. That's this idea of our mechanical advantage, our simple machines, and why it's so useful. Well, that tells us that the force times the distance that A moves, side A moves, has to equal the force of B times the distance that side B moves. Now, I'm told, we know the forces, we've already been given them. I'm told that force A is 2450, and that I raised that motor by 0.06 meters, 6 centimeters. So if I apply 300 newtons of force, how far down did I have to push? All right, so how far down do I have to push to get this same work done? And when I solve for how far down I have to push, the distance on that side, I find that that is equal to 0 0.49 meters. So I have to push about a half a meter in order to raise this side 0.06 meters. It's the same amount of work to be done. All right? So that tells us that if I raise this side by 0.06 meters, I'm going to lower this side by 0.49 meters. All right? So you can imagine now that we have this situation with our board, which tells us that these two heights together give us this whole length. All right? So I have a triangle to begin with where this side is 0.55 meters. And I can therefore get my angle here. So what is the angle that this board is at, which defines where that fulcrum is? So if I determine this angle, I know that this is 2 meters. Remember, that's the length of the board. The sine of the angle is my opposite, 0.55, over my hypotenuse of 2. And so my angle is equal to 15.96 degrees. So this angle here is 15.96 degrees. All right, well, why is that important? Why is that important? Because if this angle, I'm going to go ahead and erase this work that's been done. Oh, goodness, hang on. I'm going to look at our two triangles here. Okay. So if you imagine this, I'm just going to redraw this. This is our original, okay? And now I've raised this up by 0.06. And this has lowered by 0.49. We've determined that this angle is 15.96 degrees. And I want to know where this fulcrum sits. All right, I want to know where that fulcrum sits. I want this length L. All right, so where that rotation point is to raise that by 0.06 degrees. And so I'm looking for this length L. And so that length is the adjacent side. So the cosine of the angle, remember, is the adjacent over the hypotenuse. The tangent, that is not what I want to do. I want to know where to put this fulcrum along here, not along at that location. I apologize. I'm doing the other problem in my head. Okay. Well, we could put it along the ground or along the board. So we could either find this hypotenuse. This is the length that we might be interested, or we can talk about how far along the ground do we want to put it. This is the length we might be interested in. So it's all about where you're kind of putting your pictures. So if this is the length that we're interested, how far along the board do I need to put, along that lever, if this is what we're calling the lever, do I need to put that? We want to determine that hypotenuse, and I know the opposite side and I know the angle. So we're going to look at our sine relationship. So the sine of the angle is equal to the opposite over the hypotenuse. So that tells me that the hypotenuse is the opposite over the sine of the angle. Well, my side, oh, that should not be 2 zeros, that's a 6. 0.06 divided by the sine of my 15.96 degrees. And I find that that length up the board is equal to 0.21 meters. So we want to put that fulcrum 0.21 meters along the length of the board. 0.21 meters along the length of the board. That's pretty close to where we would want to put it if we looked at the lever arm just along the base. But if we want to also consider where to put it on the ground, if you had that board flat, you'd want to put it at that 2.1 meters of the board so that you could raise that board, that 2.1 meter location, and get the even work done. So 2 ways to interpret this problem. One is sort of where along this 2 meter board do we put it in order to get that rise of 0.06 and that drop of 0.49 meters. Or considering, okay, well, let's say if we're interpreting the lever arm being between the 2 points of action, we do a torque analysis. So 2 different ways to maybe interpret this problem. We solved both of them. Good job.